Good afternoon, everyone. My name is Rajdeep, and I'm joined by my partner Yueheng. We are machine learning associates at SSEC, and we have been working on identifying attack campaigns from network alerts in the past few months. So, first of all, what is SSEC? SSEC is a cybersecurity company whose job is to provide other businesses with easy-to-use, effective solutions. And one such interesting product is basically helping security analysts identify attack campaigns. Now, this is the product on which we both work on. So, what is an attack campaign? Attack campaign, also called attack flow, it's basically a series of malicious activities carried out by cyber criminals in order to breach the security defenses of an organization, maybe to place malware, to steal personal information. Attack campaign is complicated. It has to be planned and requires strategic execution. So to briefly describe the motivation of identifying attack campaigns, the thing is nowadays almost all companies, they use internet to send emails, share or store data. So numerous events occur almost every second within a company's network. So these events or alerts, they can be simple emails being sent out across different computers, or maybe some hacker is performing a complex DDoS attack. So it is important to basically be able to identify these malicious activities from this group of alerts. This is the job of cybersecurity analysts. Now, where we come in is basically to help these analysts quickly and easily identify such threats and identify the attack campaigns from the huge number of alerts that we have in a network. The main goal is to basically reduce their turnaround time. So to briefly summarize what we have in a problem statement is that we have a large set of events, maybe emails being sent out, some communication across different computers. We need to group them, and after grouping them, we need to identify the malicious ones. After we have identified the malicious events, we need to generate possible attack campaigns from this. To solve this problem, we take a two-step approach. The first step is clustering, wherein we have these low-level events which need to be grouped into high-level clusters. And each cluster basically should represent a stage in an attack flow. The second step is sequencing, where the group clusters should then be formed into chains, and a chain will denote an attack sequence. One thing to note is that the order of clusters in a chain, it's important. The most important thing behind the solution was that the system that we should design, it should be interpretable and scalable. It should not be a black box like a deep neural network. So I'm going to hand over to you, ma'am.
Thank you, Rajdeep. So this is a visualization of the two-stage pipeline that Rajdeep just touched on. Now let's go into details of this pipeline with a very simple hypothetical attack situation. So we start with event data, which are interactions between devices in a network. So in this example, there are internal servers and then outside laptops, and they're all talking to each other. One arrow represents like one message or event or communication, and it has a timestamp associated with it. The task of the clustering model is to identify related interactions and to group them into clusters that represent a possible stage of attack. So, for example, in this in the example below, we can see that the red edges are a bit suspicious because they're all outside actors connecting to one server in a very dense amount of time. And so we report it as a cluster with the associated information. And we say that this might be a denial of service attack, which is when lots of outside actors are trying to request service from a server at a very short amount of time to make it unavailable to its intended users. And the output of the clustering model on a larger scale includes many clusters many cluster data, and it roughly looks like this. And the task of the sequencing model is to take these unordered clusters and to order them into possible attack sequences. So for example, here, cluster 3, which is stage 1, could be a predecessor of cluster 12, stage 2, and this can be followed by cluster 15, which is stage 3. And this is just one possible attack sequence. The goal of the sequencing model is to output many of these possible sequences, and the final output looks somewhat like this. So now that we have an idea of how the general pipeline look like, we will go into detail for each of these components. So let's start with event data. We have mentioned that each event contains a source device, a destination device, a timestamp, and then information associated with this communication. We abstract this into a dynamic graph on the network. So nodes are devices in the network, and edges are events between source and destination with timestamp and associated features. And our objective is to group massive amount of edges into clearly defined clusters. So to do this, we first turn the nodes and edges of this graph into vector embeddings, and then we do density-based clustering on the embeddings. So when I say embedding, I just mean that we need to turn the graph structure into a numerical vector so that the downstream model can understand it. And in this process, we need to take into account the graph structure, the node and edge features, and as well as the timestamp of the edges because it's a dynamic graph. And then we do cluster on this point. So a clustering is just when we have a bunch of points in the vector space, we want to group together points that are close together. However, the most common clustering approach, such as k-means, have some shortcomings that make them not applicable to our use case. So for example, they need that we know the number of clusters in advance, which we do not. And also for common clustering approaches, each point needs to be assigned to a cluster. But in our use case, the majority of the points are noise, and our clustering approach should be able to identify noise from the real ground truth clusters. And finally, they only allow clusters of spherical shape, but we need clusters of arbitrary shape. So as a result, we adopted density-based clustering to deal with the above mentioned issues. So our development trajectory is roughly as follows. We first selected the embedding model and the density-based clustering model. This is based on prior checkmark experiments. And then we try to figure out how these models work on our data and also how they interact with each other. This is done through extensive visualizations and experiments. After that, we iteratively improve upon this pipeline to add on complexity. So our results include we implemented improved modules of these two mentioned models so that they are more tailored towards our use case in both logics and implementation. And in the second iteration, we did some more drastic changes to the model. So for the embedding part, we got rid of the default link prediction task as the self-supervised training task. Instead, we use contrastive learning techniques from computer vision. And this resulted in a 53% improvement on performance and also faster training and tuning. On the clustering side, we adopted on the clustering side, we adopted a data stream method so that now we can process new data incrementally by batches instead of having to retrain the whole module for each new batch of data. And this is important because our use case include like constant processing of incoming data. And this is a quick visualization of the clustering model. So the left side is our baseline performance. The right side is what the model gives now, and this is on a data set of around 10K edges. We can see that the clusters on the right-hand side are much more defined. And with that, I'm gonna hand over to Rajdeep.
Yeah, sure. So basically now that we have covered the clustering model, so what we have is a group of clusters, and each cluster have the following features. So it has the ID, the list of alerts that has been clustered, the average timestamp, and maybe the IP addresses of the devices involved. So what is the goal of sequencing? The idea is to basically sequence these clusters and form chains, and each chain should represent an attack sequence. So as you can see, chain 1, chain 2, up to chain T, these can be some of the sample chains which have been generated by a model. And one important thing to note is that within a sequence or chain, the order matters. So the sequencing model is based on a variable length Markov model. Now, a Markov model by its nature is probabilistic. As a result, the outputs will vary across different runs. In order to get as many chains or as many sequences as possible, we need to run the model maybe k times. Now, k here is a hyperparameter. So I've been talking about Markov model. Now, what is a Markov model? So suppose the weather of Toronto, it can have only 3 states. It can be either sunny, cloudy, or rainy. So today, for example, okay, it is sunny now, but it was cloudy before. So okay, so now it's sunny. So what is the probability that tomorrow it will be cloudy given today is sunny? So that's 0.1. So this is a Markov model where the probability of the next state depends only on the previous states that came before it. So moving on, what we have on the left is a transition diagram, and the same information can be conveyed using a transition matrix. So the 3 weather conditions that we have, sunny, cloudy, and rainy, they are called the states of our Markov model, and the probability of, say, today's sunny weather transitioning to tomorrow being rainy, that's 0.1. So now how do we use Markov for sequencing? What we do is basically we replace the weather conditions with clusters. And we still have the same transition matrix, and the values within the matrix determine what is the probability of, say, cluster X transitioning to cluster Y. So how do we generate a single sequence from our Markov model? Suppose we start with cluster 2. So now our chain has only one element, which is cluster 2. So from the diagram, it can be seen that the transition probabilities from cluster 2, they are 0.3, 0, and 0.7. From this probability distribution, we sample the next cluster. Suppose the next cluster that we sample is cluster 3. And now we have in a chain cluster 2 and then cluster 3. Again, what is the transition probabilities from cluster 3? That is again 0.5, 0.5, and 0. So now the question is, do we sample from this new probability distribution right away? We do not. What we do is we combine the transition probabilities of both cluster 2 and cluster 3 while giving a higher priority to cluster 3. So the idea is the priority will decrease as we go away and towards the beginning of the sequence. So in order to calculate the effective transition probabilities, we do a weighted sum, which can be seen as follows. So now what we do is we keep repeating the same process. We keep sampling and we're adding more clusters to the chain. Now the question is, when do we stop? We stop when the probability of a chain or an attack sequence is lower than a threshold T. Again, T here is a hyperparameter that we need to tune. So now we have a single sequence. How do we get multiple sequences? So if you remember, we chose cluster 2 as our head in our previous example. We could have chosen cluster 3 as our head, or maybe cluster 100 as our head, and generate sequence based on it. That's one way to get multiple sequences. Even within the same head cluster, since the Markov model is probabilistic, and since we keep sampling from the same probability distribution, we might end up with different chains because sampling in its nature is random. So maybe in the first run, the Markov model might sample cluster 3. In the second run, the same Markov model might sample maybe cluster 1. So there will be different chains. So at the end, the output of the sequencing model would give us these multiple chains where each chain would be an attack sequence or an attack flow. Now, there were some challenges that we faced in our sequencing task. The first thing is memory optimization. In a Markov model, we need to use transition matrix. And for our task, it was large and sparse. So what we did to reduce the memory footprint, we used sparse representation of the matrix. Second, since we needed to run the Markov model multiple times to ensure total independency, we had to make deep copies. Again, that increased the memory footprint. And so we had to resolve to manual garbage collection to remove the unused class instances from RAM. The second challenge that we faced was the lack of data. And for that, we took a hybrid approach. Since we have domain knowledge, what we did is we used that to predefine the transition matrix and then use the limited data that we have to tune the values in the matrix, say to a certain extent, maybe plus minus 20%, plus minus 30%. And following that, there are some, again, next steps that are work still, that can be done to improve our model. So the thing is what we need to do is we need to find the optimal set of hyperparameters. Now the goal is these parameters, they should not be they should not be too fine-tuned on one data set, but rather it should generalize well on multiple data sets. So the main achievements that we managed to maybe achieve in sequencing is basically we implemented a package or a library for a variable and Markov model, and it has already been integrated into the existing pipeline. The existing sequencing logic that SSEC had, it was based on SQL and it only generated pairs of clusters. The new approach can generate sequences with 10 plus clusters. We also implemented a custom loss, which has 3 custom components to capture the global context, local context, and order context of the chains. Finally, the sequences that our model can generate now, it covers more than 50% of the data set. Thanks, man. Okay. Thank you. And
so in the beginning, you mentioned the shortcoming of traditional clustering methods, which is the noise it's not supposed to be assigned to a cluster. So I wonder how your approach dealt with noise.
Sure. So for density-based class, so in the traditional clustering, that depends on centroid. So you give it like a pre-specified amount of clusters, and then usually the centroids are selected with some domain knowledge as well, and then basically the cluster keep growing among the centroids. So in our case, the noise is pretty like uniform across the embedding space. And if we use these traditional methods, then they will get added to those centroids because they will be near some centroids. So for density-based clustering, the cluster are defined by like density, as the name suggests. So like if an area is dense, then we just count that as a cluster. As a result, if like the noise are uniform, so and sparse, then like their general density wouldn't make them count as a cluster.
Oh, that's really interesting. I guess a follow-up is on what scales are you looking at? Because noise, if you look at locally, it may not be uniform, but if you look at an appropriately large scale, it is uniform. So is there a scale that you found out that was on the scale the noise looks quite uniform?
Yeah, totally. That's a good question. So it's actually, so for density-based clustering, there are like, I guess, 2 important parameters to control like what's the diameter of the cluster and also the density of it, like how dense do we count it as a cluster. So we need to fine tune those parameters so that like it's basically answered by fine tuning to see what's noise and what's not.
Nice. Okay, thank you.
Yes.